Okay, so today, as I said before, we are going to talk about the different types of covalent bonds. So if you look at this handout here, we've been talking about ionic bond. We've been talking about covalent compounds. Now, when we're talking about covalent bond, do keep in mind a couple of things. Yes, we're talking mostly about things that are non-metal combined with non-metal, but there are different types of covalent bond. Now, there's this table here on your handout, okay? 0, 0.4, 1.7, 4.0. What on earth does that mean? Now, I think the textbook have a much nicer page that shows what those things are. So if you look at the textbook, yes. So if you take a look at your textbook, page 61, on the top corner of it, you have this really nice color scale. Okay, this really nice color scale. Now, again, if you look at the scale here, look at the axes, you have delta En. What does delta means? I know it's math-ish, but also like math, physics, certain part of chem. What does delta means? Anyone? Yes. Differences. Thank you. Differences. Okay. So but you didn't say anything. So you know what it means, but you didn't say anything? Well, I was guessing. Okay, good guess. Okay. So what it means is this. You're talking about the difference of electronegativity. So without looking back at your old notes and whatnot, what is the definition of electronegativity? What's a definition of electronegativity? Yes, Greg?
It's a way of measuring how ions attract electrons.
Okay, so it's from a periodic table. We want to see how much a particular atom attracts electrons. Yes, Aviva? Perfect. Okay, so the ability of an atom, a certain atom, attracting the valence electron in a covalent bond. Remember, probably last week or so, or the week before, I was doing this talk about like covalent bond versus ionic bond, and I was saying in covalent bond, me and Manodin were sharing a pencil, but if he likes pencil more than I do, then the pencils will be closer to him, even though technically we're sharing. He didn't take my pencil. Okay? Do you guys remember that? So electronegativity, going back there, is also a relative value. It's also a relative value. Okay. So coming back here, I think there is a section that talks about electronegativity. So will be good to refer to it. So in this case, electronegativity, we're talking about how much a strong pull or attraction to the bonding electron. Okay. A stronger pull or attraction of bonding electron. So how does this work? Take out your periodic table, the one that you have. If you look at your periodic table, I'm going to focus my screen here a little bit more. This value here on your periodic table is the electronegativity of a particular atom, right? Of that particular atom of the elements. So let's use some of those stuff that we were using before. So in this case, we have nitrogen and hydrogen. Okay, you have NH3. So you have nitrogen, you have hydrogen. They are all forming covalent bonds. But you want to see what kind of covalent bond it is. Are the electron closer to sodium, to the nitrogen, or to the hydrogen itself? Now, what you do is this. You might want to, you can probably copy it down here. So I'm just going to rewrite this part. So in this case, you look at the electronegativity, En, of nitrogen. So here, nitrogen has electronegativity of 3.0. Okay, 3.0. Hydrogen, on the other hand, have an electronegativity of 2.1. Okay. So when you're trying to find the differences of that, delta En, delta means the difference in between the two values, would be 0.9. Okay. So the difference of electronegativity on a nitrogen hydrogen covalent single bond, it will be 0.9. What it means is this. If you look at this scale, 0.9 would be just a little bit below 1.0. So in this case, this bond that you have between the nitrogen and the hydrogen will be considered polar covalent. Okay, polar covalent. Okay. So this will be considered a polar covalent bond. What it means in this situation is that the electrons in that covalent bond will be closer to which atom, nitrogen or hydrogen? Yes, Ash? Nitrogen, why? Perfect. So the electrons will be closer toward nitrogen than hydrogen because nitrogen is more electronegative than hydrogen. Okay? Electronegative than hydrogen. Okay? So the electrons will be closer to here. So you can kind of use an arrow kind of above the bond to show that it's more closer towards nitrogen. Okay? Now, do keep in mind, this calculation is only between one atom with another atom. You will still need to do, it's not like in consideration of all three. Okay? Are we good so far? Let's do another one. Maybe not phosphorus. Yeah, let's try that. Okay, so in this case, we're going to try the other example during our quiz is PCl3. PCl3. So again, we drew the Lewis diagram. This is the reason why you need to be pretty good with the with drawing the Lewis structure. So you guys use your periodic table. Yeah, I'm not going to read it. Tell me, what is the electronegativity for phosphorus? Someone put up your hand before you speak. What's the yes, Sage. For phosphorus, electronegativity. Yes, Tonian. 2.1, thank you. Okay. Chlorine. Yes, Ewan. 3.0. Okay. So again, if you look at that, the difference between the electronegativity, that's 0.9. So again, it is 0.9. It is also polar covalent. Yes.
Isn't it negative 0.9 when you subtract 3 from
Yeah, this scale here is absolute value, so you don't do the sign. Yeah, it's just absolute value difference. So whether it's 3.0 minus 2.1 or 2.1 minus 3.0, we're only looking at the absolute value. Okay. Yeah, the scale doesn't provide the negative. So in this case, it is polar covalent bond between the phosphorus and chlorine. Now, where would the electron be closer to then? Who would the electron be closer to in this situation? Yes? Chlorine? Why? Good. It's more electronegative than phosphorus. They want the electron closer to it more. So the electrons will actually go towards the chlorine in this case. Are we good so far? So, let's do one more. So let's just say O2, you have a double bond situation going on. But either way, whether it's double bond or single bond, it's still the same. What is the electronegative of negativity of oxygen? Look up on the periodic table. Yes? 3.5. Now, both atoms are oxygen. So in this case, what will be the difference between them? That will be 0. There's no difference in terms of electronegativity between those two. So in this case, in that situation, you will have a perfectly non-polar covalent bond. Right? So when you have those diatomic elements, I have no clever or brilliant friend or Hofbringer or whatever you use to remember it. Those would be perfectly non-polar covalent. The electrons will be perfectly shared right in the middle between the two different atoms or two different nucleus. Any questions on this? Now, yes?
How does it affect the strength?
The what?
How does it affect the strength of the bond?
How does it affect the strength of the bond? It depends on what you are, like if you're talking about the number, how easy or difficult for it to break. Typically bond, like how strong the bonds are, it really depends on which two elements, as well as single or double bond. I will have to double check that. Usually I don't get that question. Okay. Typically, if you have like double bond or triple bond, it takes more energy to break than the single bond itself. Yeah. Now, a couple of things. This scale, do you need to memorize this? And the answer is no, you never need to memorize this. Okay. If on the tests and situation, I will provide this scale to you. Okay. But you, of course, need to know how to use it. And of course, during a test, you need to remember where you find your electronegativity value on your periodic table. Okay, so do remember it's right here. Now, so typically when you have a situation where you have electron being closer to one side than the other. Now let's coming back to the nitrogen here. If the electron are more closer to the nitrogen than hydrogen, which one do you think will be more negative? Yes? Nitrogen. Okay. So even though the whole entire molecule as a cell on its own, like overall, this whole molecule is neutral, but because the electrons are much more closer to the nitrogen than to the hydrogen, you have what you call a partially negative side. Okay, so nitrogen will be partially negative, and the hydrogens will be partially positive. Okay, so you guys see the symbol here? How you write the symbol? It's like this, or this. Okay, or so let me repeat this again. Because the electron in NH3, the electrons are closer to the nitrogen than toward the hydrogen. So even though overall the whole molecule is neutral, but because inside the molecule the electrons are closer to nitrogen than hydrogen, the nitrogen will be partially negative or slightly negative, and the hydrogens will be partially positive. Are we good? So let me just write it down. Okay, so make sure you add the symbol here. While NH3 overall is neutral, will be partially negative, and hydrogen partially positive. Okay. How are we doing? So make sure you have that. Now, the opposite here is true. In PCl3, because the electrons are much closer towards the chlorine than to the phosphorus in the middle. Because of that, all three chlorine will be partially negative, and the phosphorus in the middle will be partially positive. So overall, the molecule is neutral, but these guys like the electrons more, so these guys will be partially negative. You have a partially positive part or side of the molecule itself. Any questions? Now, in a situation where you have a non-polar covalent bond, that's a situation where you won't have these partially negative, partially positive part, because electrons are perfectly in the middle or just slightly off. It's not quite enough to have this partially positive, partially negative side. Okay. So in non-polar covalent bond, because the electrons are perfectly in the middle or just slightly off, it's not quite enough to have a partially positive, partially negative side. So this one won't have that situation. Any questions so far? Now, it's important for you to be able to figure out what type of bond it is, okay, polar covalent, as well as if it is polar covalent, where would the partial positive and negative charge be? Because tomorrow we're going to start using that, as well as the shape of molecule to figure out if a molecule is actually polar molecule or a non-polar molecule. Okay, polar molecule or non-polar molecule. Questions? Okay, so if there's no questions, what I want you guys to do on textbook, in the textbook, page 63, question number 10, again, there's a list of, there's 8 different pairs of elements. So you are to use the scale to figure out what kind of bond would it be, okay? This one would also be including mostly ionic, okay? So make sure you do this. That will be for homework. Again, that will help us to build up to tomorrow in terms of figuring out whether something is polar or non-polar. Okay, page 63. Okay, page 63, number 10. All. Okay. There's no handout for this one. I'm gonna also add an Edpuzzle video so you can watch it beforehand. So in this case, tomorrow it will be, in terms of polar versus non-polar molecule, it will be a lot smoother. Okay, so I'm gonna add a link shortly. Okay. Any questions? Okay, I'm gonna turn off the recording.